Welcome. We're about to dive deep into the statistical engine that powers, well, pretty much all of modern data science and machine learning. We're going to go way beyond just using the algorithms. We're going to really understand the probabilistic structures that generate the data in the first place. So let's just start with the biggest question of all, the one that frames this entire journey. How does a machine actually learn from data? I mean, it can feel like some kind of black magic, right? But the answer, it turns out, is pure mathematics. And today, we're going to build a blueprint for that statistical engine together. And here is our roadmap for that journey. We're going to start with the toolkit, which is all about understanding how variables talk to each other. Then we'll move to the limit, where we'll see how beautiful, predictable order can emerge from total chaos. And finally, we'll assemble everything into the model. That's our engine for actually learning from data. Okay, so let's dive into part one. Before we can even dream of building a model, we need the basic tools. We've got to have a way to describe how different pieces of information relate to one another. So the first tool in our kit is conditional probability. Now, the core idea here is actually super simple. Our beliefs change when we get new information. Think of that whole 3D hill as all the possibilities. But then, if we learn a new fact, let's say we find out our playing card is a face card, it's like we take a sharp slice right through that hill. Suddenly, our world of possibilities gets a lot smaller. The probability of drawing a king is no longer 4 out of 52, it's now a much better 4 out of 12. We've updated our belief based on new evidence. And don't worry about the symbols here. F of x comma y is just the probability of both things happening together, while f sub x of x is just the overall probability of x happening all by itself. Well, that leads us to the next logical question, doesn't it? What happens when that new information is completely, utterly useless? When knowing one thing tells you absolutely nothing new about another? And that brings us to this absolutely crucial concept, independence. Formally, it's when the probability of two things happening together is just their individual probabilities multiplied. It's really the ultimate test to see if two variables are truly, completely unrelated. Now, this slide, this is where that abstract idea just clicks. Look at the left side with dependent variables. See how every slice we take gives us a totally different shape for y? But now look at the right for independent variables. Every single slice is identical. Knowing x gives you zero new information about y. It's a perfect visual for what independence really means. Okay, this brings us to a huge, and I mean huge, pitfall. We often use correlation to measure the linear relationship between variables, but you have to be so careful, because while independence does guarantee zero correlation, the reverse is absolutely not true. And this visual shows you why perfectly. Look at that circle of data. If I tell you the x value, you know a ton about where y can be. They are super dependent on each other. But because the relationship isn't a straight line, the linear correlation is zero. So please, burn this into your brain. Never, ever assume that zero correlation means there's no relationship. All right, we've got our toolkit for how variables interact. Let's move on to the next section and see what happens when we scale things up, when we start looking at massive amounts of data. This, my friends, is where the magic really starts to happen. You know, in the real world, we almost never get to see the whole picture, the entire population. We just get to see little samples. But here's the beautiful thing. As we collect more and more and more data, our random noisy samples start to converge. You can see it right here. What starts as a jagged, unpredictable mess when n equals 1, it just smooths out and takes on this predictable shape as our sample size grows. Randomness starts to look like order. And the first mathematical guarantee of this order is the law of large numbers. This is the absolute bedrock principle that makes things like polling and scientific sampling actually work. As this graph shows so clearly, the running average might be all over the place at first, but as we add more trials, it just inevitably settles down and homes in on the true underlying average. It's a mathematical promise. More data gets you closer to the truth. And now for what is frankly one of the most powerful and, honestly, beautiful results in all of statistics, the Central Limit Theorem. It basically says that if you take enough independent random things and add them up, the distribution of their sum will always, always, always tend toward that classic Gaussian bell curve. And here's the kicker, it doesn't matter what their original distributions looked like. This incredible universality is why the bell curve just shows up everywhere in nature and in data. And this right here leads to such a profound insight. Why do we so often assume the errors in our models are Gaussian or bell-shaped? It's not because we think nature itself is shaped like a bell curve. No, it's because we believe that our errors are the result of many, many tiny, independent, unobserved factors all added together. And what does the Central Limit Theorem tell us about the sum of many small, independent things? It converges to a Gaussian. It's a beautiful piece of logic. Okay, let's move on to our final section and see how all of this builds. With our toolkit for relationships and our understanding of how things behave at a large scale, we are finally ready to assemble the engine. This is where we stop just describing data and we start building models that actually learn from it. A core method for doing this is called maximum likelihood estimation, or MLE. And the whole philosophy is kind of like reverse engineering the data. We just ask a simple question. Given the data I actually saw, what setting for my model would have made this outcome the most likely, the most probable? The biased coin example is just perfect for this. If we see 7 heads and 10 tosses, well, the parameter that makes this data most probable is, pretty intuitively, a probability of 0.7. We just find the very peak of that likelihood curve. But what if we already have some knowledge before we even see the data? Well, that's where Bayesian estimation comes in. It gives us a formal mathematical way to combine our prior beliefs with the new evidence from our data, which is the likelihood. The results, which we call the posterior, is this really sensible compromise between what we thought before and what the new data is telling us. It's a way of updating our beliefs as new evidence comes in. And here it is, a huge aha moment where it all comes together. Remember linear regression from way back when, where you try to minimize the sum of the squared errors? Well, this proof shows that doing that is mathematically identical to doing maximum likelihood estimation on a model where you assume the errors are Gaussian. Think about that. The Central Limit Theorem gave us the reason for the Gaussian assumption, and MLE gives us the method to find the best fit. This connects 2 of the most fundamental concepts in all of statistics. It's amazing. But that assumption you make really, really matters. You can't just slap a Gaussian model on everything. Linear regression is fantastic for continuous data, but it's just awful for count data. It can even predict negative counts, which is physically impossible. For counts, you need a different probabilistic assumption, like the Poisson distribution. The takeaway is this. Choosing the right underlying model is absolutely critical if you want to get sensible results. So let's just take a step back and put this all together. We've journeyed all the way from single variables to building complex models. It's time to look at the complete blueprint that we have just constructed. This pyramid just perfectly summarizes our entire explainer. At the very bottom, you have the bedrock, probability theory. That's our concepts like independence and the Central Limit Theorem. Built right on top of that is inference. That's our methods like MLE and Bayesian estimation that let us learn parameters from the data. And only then, at the very top, sits machine learning. See, it's not magic. It's just the application of these foundational layers. And the connections to the stuff you hear about today are incredibly direct. A neural network? At its heart, it's just a very, very complex way of modeling a conditional distribution. The loss functions we use to train them, they're almost always derived directly from maximum likelihood. And regularization techniques like L1 and L2, those tricks we use to stop our models from getting too complex, that's really just a form of a Bayesian prior belief. Understanding these foundations turns model fitting from a black box into true statistical modeling. So before you go, let me arm you with 4 crucial warnings. First, and always, correlation is not causation. Second, as we saw with that circle, zero correlation does not mean independence. Third, be super careful that your data points are actually independent. With something like a time series, where today's value depends on yesterday's, standard models can completely fall apart. And finally, be wary of MLE on small data sets. It has a tendency to blindly chase the noise instead of the signal. So there you have it. We've deconstructed the entire engine room of data science, from the simplest ideas of probability all the way to the foundations of machine learning. You now have the blueprint. The only question left is, what are you going to build with it?